Hello everybody and welcome to the NPTEL online certification course on microelectronics devices circuit. We start today with CMOS inverter basics part 4. What we will be doing in this case is we will be looking into from the time when we left in the previous case. We saw that in the previous introduction that for an optimized design in terms of reduced delay between primary input and output, the gate capacitance of the middle transistor or a middle inverter in a chain of inverter should be in a geometric progression of the subsequent and the precedent inverter. So, if you have 3 inverters, so what I wanted to say was that if you have got 2 inverters, so you have got 1 inverter, 2 and then 3 here, right. Then if you want that the delay should be minimized, then try to keep the input capacitance of this inverter, right, J, let us suppose it is J, to be equals to square root of C in J plus 1, this one, multiplied by C in J minus 1, which is this one, right. So, we have seen that, and therefore, how we got it, we have derived in the previous lecture this basic concept, that if you want to do this you have to do these basic concepts. So, let me start from there and show to you that therefore, the optimum size of each inverter, jth inverter, is the geometric mean of its neighboring inverters or neighboring sizes, right. It should be neighboring inverters as well, right. So, then so what we are telling you is that jth inverter will be basically if you are able to fix its value of input capacitance to be equals to this, then possibly you will get a reduced delay. Now, this means that each inverter is sized up by a factor of width f with respect to the preceding case has the same effective fan out, which means that you see. So, what I was saying was that you had inverters like this chain of inverters and it ended up at nth inverter, and the last one you had a load capacitance CL and this was V out. So, if each of the inverters gives you a, this should be geometric mean of this thing, similarly this should be geometric mean of this and this, then what we finally get is that if you take overall chain, do a cross multiplication, then you get CL by CG1 square root of nth root, this will be the function f, fine. I think it is clear to all of you. Why? Because as I discussed with you that as you move from the first inverter to the last inverter in a chain of inverters, then you have to progressively size it up as you go from lowest to highest value. But how you will the rate at which you will be sizing it up will determine whether you are optimizing your design or not. Now, if your last inverter was terminating into a load capacitance whose value is equals to CL and the first inverter was basically equals to CGI input capacitance, then CL by CGI or CG1 nth root of that will be your f factor, which is basically your sizing of factor f. So, if this is capital F which we term, let us suppose the ratio is termed as capital F, also referred to as fan out, electrical fan out, then we refer to small f to be equals to nth root of capital F, which you see in front of it, right. Once you have known this, you just have to feed it into your original equation of chain. So, you get Tp equals to y NTP 0, because see, if each inverter has a intrinsic gain, intrinsic delay of Tp 0, and if you have n such chain, obviously the delay will be obviously larger than NTP 0, and therefore you see NPT 0 coming here as a quantity. You also have therefore this quantity therefore coming up here, right, divided by gamma. From where I got this? From the previous our previous understanding we got this, that if this is, so I was saying it is f by gamma, if you remember. Now, this f is nothing but nth root of f, where capital F is given by this quantity, and therefore I get this by gamma to be equals to Tp, where Tp is the overall delay this thing. So, f represents the effective fan out, right, and we get effective fan out. Now, what you do is that you need to differentiate the previous equation, which equation? This equation Tp with respect to n, right, and make it equals to 0 and then maximize it, minimize it, right. and then if you set equals to 0, I get this equation into consideration, that gamma plus something minus nth root of f by n equals to 0. Now this typically means that it has been shown that, therefore if you plot f or if you plot gamma on the x axis and you plot the delay on the y axis, typically you get a curve something like this, right. You will get a curve something like this. Somewhere around, if you fix gamma equals to 1.5, you will get a delay of approximately 3.5 maximum delay, which you set, which you set, or approximately 4. So in common practice, it is always advisable to keep the optimal fan out as equals to 4, right, because this is what you get. So you approximately 3.5 to 4 you get if your gamma is equals to 1.5. Gamma is basically your factor which gives you the output ratio of your capacitances. Now with this knowledge we therefore tell that the optimal fan out should be approximately equals to 4, which means that if a single transistor is there and you want to optimize the output, you just have to have fan out of 4 available with you, right, and that will give you the best results as far as this design is concerned, right. Let me now come to an important topic. So we have understood what the delay is all about, how to size a transistor to get the optimal delay. Now a very important property of inverter is that it is basically switching, right, from on to off state or 0 to 1 state in the output side. So since it is switching back and forth from a high value to a low value and vice versa, there is always an energy which is being dissipated or a power which is being dissipated due to the switching action, and that power is basically known as dynamic power, right. Typically a transistor or an inverter will have 3 types of power. One is known as dynamic power, right, one is known as, the other is known as basically static power. This is static power, and the third one is actually referred to as a short circuit power. We will explain each one of them individually, but let us first understand dynamic power, right. Dynamic, as the name suggests, is basically the power which the CMOS dissipates or draws from VDD rail when you do have a input which is varying from 0 to 1 and 1 to 0. So you do have switching characteristics which is available with you. If you see, then as all of you are aware of, that energy taken from a supply is, suppose EVDD is the energy taken from the supply VDD, must be equals to 0 to infinity I current multiplied by voltage. V into I is basically the power which you get, and if you integrate from 0 to t in time domain, so what will happen is this if you break down I and V, I get CL times VDD into integral 0 to VDD dV out, right. If you solve it, I get CL VDD square, right. So if you remember from our basic inverter, so I had this, right, and I had this and then this. So every time you are actually charging this capacitor, you are taking half C VDD square, where C is this capacitance, power from the VDD rail, right. In the next half cycle, when this was closed, the same used to go here and you just remove this half C VDD square. So you take half C, so in one cycle you take half C VDD square and you throw it in the next cycle to the output side, you again take. So when you have input equals to 0, your capacitor charges to half C VDD square, and energy is stored as half C VDD square. From where does it come? It comes from the VDD rail, right, which is the power rail. In the next half cycle, when input is equals to 1 and output goes to 0, then the charge accumulated onto this is dissipated across the ground, and therefore it goes to 0, and therefore I get the total power dissipated is equal to half plus half is basically CL VDD square over a 2 cycle of ranges. Now energy stored or removed in a capacitor is given by, as I discussed with you, is CL VDD square by 2, because half it is there. This is independent of the transistor size. So please understand that your effectively the charging or discharging of the capacitor is independent of the size of the transistor. So it can be any size which you can choose, and you can actually have a size which is available with you. If switching activity is 0 to 1, so you see an important point is that only when your output goes from 0 to 1, right, that is the time when you are accepting power from the VDD rail. So please understand, the dynamic power which if you are not dissipating, you are getting it from the VDD rail, is only happening when your output is going from 0 to 1, because that is the point when your capacitor is getting charged through PMOS and you are drawing power from the VDD rail. And that is the reason we say P dynamic to be equals to CL VDD square multiplied by the frequency of 0 to 1, right. What is the frequency of 0 to 1, which is there with me. Now that is known as a dynamic power dissipation. Now what happens is that we have discussed this point earlier also, that when you draw the voltage transfer characteristics, right, this is what you get, this is your V in, right, and this is your V out. At this stage NMOS is cut off and PMOS is switched on, and at this stage PMOS is cut off and NMOS is switched on, and that is the reason it is grounded. But and therefore you do not have a direct path between VDD and ground. So if you at this point, if you let us suppose this is point X, at point X if you want to find out what is the output characteristics, it looks something like this, it looks like this, and then this is open and this is CH, right. So this NMOS is open and this is basically my R equivalent P, this is VDD and this is my C capacitance available with me. So which means that this is saturated and this is cut off. What happens at Y, which is this point, Y will be, this will be open and then I will represent it by a resistance here and there will be capacitance here C. So this will be then saturated and this will be cut off, fine. But these are the two extremes where you are seeing it. Somewhere in the middle, somewhere here, I possibly will be seeing that both will be acting as a current source, both will be saturated somewhere at this point, say A, at point A. As you can see, since two current sources in series is basically intrinsically an unstable situation, obviously you do not stay here for a quite long time. A small change in the input will result this A shifting to this point or to this point. But then if you are working at A, then you do have a direct path between the VDD and the ground rail. Please understand this properly, that whenever you, this is somewhere when both the devices are in the saturation state at point A. At this point A, when you are in saturated state, both are in on state primarily meaning that it is basically behaving like a current source in a saturated state, and as a result you will have large amount of current flow. So even I can represent this by a current source, both of them, right, whose output impedance is typically very large. Now this will when so there is a short circuit path between VDD and ground, right, ground, and as a result you will see a large current flowing. That current is that flow of current is given by this formula. So VDD is the applied voltage, I peak is the peak current multiplied by how much amount of time this current is flowing is TSC, a short circuit time, and therefore it is given by energy EDP, right. So PDP will be multiplied by frequency TSC VDD I peak into F. So if you go once from high to low and then you go to low to high, then you are actually traversing through short circuit path twice, and therefore it is depending on the value of this thing. TSC is the time when both the devices are conducting, right. So these are the two time which is when they are conducting. So we have discussed basically the dynamic power, right. We have also understood what is the short circuit power. Let me give static power. Static power or the steady state power is defined as that power when you are not in the dynamic position, which means that your input is not varying but it is fixed, or even your device may be in the cutoff state, right, and you expect that there should not be any current flow through the device, and I would expect to see that the power dissipation because of should be equals to 0, but it is not, and the reason is something like this. The reason is that whenever you assume that the device is off by saying that the gate voltage has fallen below threshold, but if you go to literature, available literatures, you will see that not necessarily the device is actually off when your gate voltage falls below threshold. So if your threshold voltage is say 1 volt and you are at 0.9 volt, then as per our understanding it should be off, but in reality there is some subthreshold current still available with there, and so though you think your device has been switched off, in reality the device is still on, and that gives you so small current internally, right. That is what is known as a subthreshold leakage when your VGS is less than VTH, right. Similarly, you will have thermally generated carriers which will affect your junction leakage. Remember, your base to the source and drain was reverse bias junction, remember, and therefore the depletion thickness is quite large there. But for minority current carriers, that is basically not a hill but a slope. So, if the temperature increases by even 10 degree, I would expect to see almost doubling of the value of your minority current carriers, which might result in a large current. So, these currents, which is basically the virtue of the reverse bias saturation current, is primarily because of these reasons. So, I define P stat as the static power to be equals to I stat, the static current, multiplied by VDD. So, we define P total, the total power which is with us, as equals to dynamic power plus your static power plus your this is short circuit power, right. This is that should be SC, short circuit power. So, I refer to as CL VDD square plus VDD into ISC into TSC into F0 to 1, and this is VDD into I leak, right. I will explain one important term which is well, it is not here, but I will explain it later on, maybe I will explain it here. I define a term known as activity factor, right, alpha 0 to 1, also referred to as activity factor. Let us suppose I have a inverter, right. The inverter will be easy to explain, and I have an inverter here, and my output is here, input is here. So, I just check out how many how many 0 to 1 transitions are available. So, let my input be a clock. So, I have 4 clock cycles, 1 2 3 4, 1 2 3 4, right. Now, I have a structure which is not an inverter, right, which is not an inverter, which is something, some gate, some R-bit gate, and that R-bit gate, if you look very carefully, has got this output, which means that for every 4 clock cycle, this is the clock I am giving, let us suppose, and this is some gate, very complex gate. My output is showing a 0 to 1 transition only in the second clock cycle, and it is then 1 to 0 in the fourth clock cycle. So, there is only, so for every 4 clock cycle, there is only one 0 to 1 transition. Then we define alpha to be equals to 1 by 4, and that is equals to 0.25. Fine, have you understood? Similarly, if let us suppose let me just erase this one, right, and let me just put it like this, that you do have the same clock cycle, there are 4 clock cycles, but now what has happened is that rather than 1 0 to 1, let us suppose you have 1, something like this. So, there are 4 clock cycles here, 4, 1 2 3 4. Now, you have 1 0 to 1 here, you have 2 0 to 1 here, you have a third 0 to 1 here. Then your activity factor alpha is basically 3 by 4, and it is equals to 0.75. You will ask me where it is required. Well, the frequency which you see f 0 to 1 can be written as probability of 0 to 1 multiplied by alpha. Alpha is the probability factor. So, f 0 to 1 is the frequency of 0 to 1 transitions, that is written as probability of 0 to 1 transition multiplied by alpha 0 to 1 transition. So, this is a typical formula which you use. So, I can have therefore the dynamic power dissipation to be equals to CL VDD square multiplied by probability 0 to 1 multiplied by alpha 0 to 1, right. So, that is, this is defined as, the alpha is defined as my activity factor for all practical purposes, and it gives me an idea if your design is having a so the gate structure is such that you have a large value of alpha, then you would expect to see a larger power dissipation, whereas if your gate value has got a lower value of alpha, you would expect to see a lower dynamic power dissipation for this case, right. One thing which you should be therefore careful about is that whenever you are planning to draw or design a dynamic power dissipation, it is not only important that how your design is, but what type of gate the design is. For example, I will give you a brief idea. Let us take, you take a NAND 2 logic, let us suppose you take, right. So, I have got A, B and NAND 2 logic, let us suppose X is the NAND 2 logic. So, 0 0 1 1 0 1 0 1. So, NAND gate means 0 0 will give you 0 output and 1 1 will get it, you will get 1 0 1, you will get here 1 here 0, right. Which means that I will get this to be a power consuming cycle, whereas 1 to 0 will not be a power consuming cycle, right. So, if you want to find the probability of 0 to 1, you need to find out what is the probability of 0 multiplied by probability of 1. So, probability of 0 here is basically P of 0 is 1 by 4, because there are 4 and 1, and probability of 1 is basically 3 by 4 here, 3 by 4. So, simply multiply P0 by P1 and you get 3 by 16 as the probability of 0 to 1. So, probability of 0 to 1 is basically 3 by 16, right. Now, in a NAND 2 gate, remember, therefore, if I give a clock cycle, let me say I have a NAND 2 gate, NAND 2 gate looks something like this. Right, I have a, this is a NAND 2 logic. So, this is A and let us suppose this is B. So, I have got this NAND 2 logic and this is my VDD here and this is the NAND 2 logic. So, when it is 0 0 output is 1 0 0, when it is 0 1 output is 1 1 0 output is 1 1 1 output is 0, right, and I get a NAND 2 logic here. So, what is the probability is 3 by 16 here, what is alpha? So, if I have now an input cycle which is something like this on the A side, let us suppose A and is something like this, right, on the A, and B is latched to say 1, then you can find the probability how many transitions are there in the output side from 0 to 1, right. So, if you have 1 here, it means that this is cut off, and if you A is giving, if A is initially 0, so this is on, output will be 0, as it goes high, as it goes at this cutoffs, this switches on, right, and since this is already 1, as this switches on, this goes from 0 to 1. So, this is 1. So, with one clock cycle I get 1 0 to 1. Similarly, the next clock cycle I will get 1 0 to 1, so on and so forth. So, that alpha multiplied by 3 by 16 will give you the overall probability or the frequency, and therefore, that will give you the output characteristics available to you, right. This gives you the frequency of operation of the device. Now, we define a new term which is basically power delay product PDP, and it is given by CL VDD square by 2. At this stage we need not worry about too much about it, and we define energy delay product which is PDP multiplied by TP, and therefore, CL VDD square by 2 into TP gives you the value of your EDP, which is energy delay product. So, we have two types of products which is there with me. One is an energy delay product and we have a PDP, and we try to optimize the energy we try to optimize the delay, and therefore, if you want to reduce the delay, dynamic power dissipation, what is there in your hand, a very good idea to reduce dynamic power dissipation is to reduce VDD, because if you reduce VDD you have almost a parabolic decrease in the value of your power, because it is square you are talking about, and that is the reason there is a sudden drop which you will see here in this case, right. You can also operate at lower frequency operation. So, in most of the cases when you do not want the power, you do not want a very high frequency of operation, you can actually afford to keep your F max low. Once you do that, your PDP and as well as your total power actually reduces drastically, right. And so, these are the few things which you should keep in mind as far as designing is concerned. Generally, PDP is a constant for any system. PDP and EDP are constant. So, energy delay product and power delay product are constant, which means that if the power dissipation rises, right, if power dissipation becomes high, then that can be only accommodated provided your system becomes slow. So, TP has to go down. TP going down basically mean that your system is getting faster in this case. Now, this is what you get from the power delay product, energy delay product concept. Techniques for reducing power dissipation, let me see. We can do it by, as I discussed with you, reducing power supply, reduce your switching activity alpha, and reduce physical capacitance. So, reduce CL, reduced alpha, reduced CL and reduced VDD. Once you take care of all these three, you will have a reduced power dissipation which is there in this module. But then the problem is that if you reduce VDD beyond a particular point, your current reduces and your the time taken to charge or discharge a capacitance becomes large, and therefore the tau becomes a large factor. So, you have to optimize the value of VDD to a larger extent. So, the rule of thumb is that typically the rule of thumb is that if you are working with 180 nanometer technology, your VDD should be 1.8, if you are working 90 nanometer 0.9, if you want 65 0.65, if you are working with 130 then 0.13 1.3 volts and so on and so forth. If you are working with 45 0.45, typically if not in a very layman sort of a rough back of the envelope you do it, right, and you get these are the VDD values. So, you best way to do is to reduce VDD, but then if you reduce VDD, the price you pay for it is of course that you are ending up having a lower current and therefore a larger tau, and therefore the time taken will be also larger in this case. So, let me therefore recapitulate what we did in this idea. We tried to find out the minimum what was the time taken to charge or discharge a load capacitance. We also tried to find out the optimum ratio of NMOS to PMOS for minimum propagation delay. We saw that the intrinsic delay is independent of the transistor size and depends only on the physical layout and the technology parameter. Now, in every charging and discharging, as we saw that the inverter actually loses half, only half of the energy stored is removed to the load capacitor, other half is dissipated by PMOS or NMOS, right. I think this is clear. So, what we do is that for in a single cycle take half CL VDD square is the total energy I take, half I dissipate to the ground and half of it is dissipates through PMOS and NMOS sink. Power consumption is dissipated by dynamic power during switching period. So, we have a switching period. How can you reduce power? Three techniques are available: reduce your VDD, reduce your alpha switching activity or reduce your CL. Reducing your VDD not a very good idea beyond a particular point, because your current will be therefore reducing and your delay will be increasing, right. So, these are the few important takeaways from this module, from this lecture of in inverter. Why was this important? Because now since you know how an inverter you can optimize its power and delay, you can now therefore do small modules of NAND gate, NOR gate, XOR gate using CMOS technology, right. Maybe we can do it in the next time and show it to you how it works out in those domains, and then optimize using sizing we optimize to get the minimum delay and the highest speed, or we do an optimizing of a PDP and ADP of the delay, fine. With this, let me thank you for your patient hearing. Okay.